Good afternoon, everyone. Thank you for coming to the first monthly webinar of the 2DCC. I am Kevin Dressler. I'm the Operation and Facilities Director for the 2DCC. Today we're going to have an overview of the 2DCC MIP for potential users, and the seminar is going to be given by Dr. Joan Redwing. I will let you know that this webinar is being recorded. This is supported by an NSF grant, so we want to have the broadest dissemination. You may ask your questions during the presentation in the chat box. If you don't want everyone to know that you personally asked the question, you can send it directly to Kevin Dressler privately, and I will collect them. If you send it to me privately, I will know that you do not want your name revealed. So welcome to the webinar, and Joan Redwing will start.
Okay, thank you, Kevin. So first of all, I'd like to thank everyone who is listening to this over the internet for joining us. This is the first webinar from the 2D Crystal Consortium, and you'll hear me refer to it as the 2DCC. So that's our abbreviation for it. And as Kevin mentioned, my name is Joan Redwing, and I serve as the director of the 2DCC. And I'm also a faculty member here at Penn State in the Material Science and Engineering Department. So what I'm going to do today is I'll give you an overview of the 2DCC, including information on our facilities and the user program for those of you who may be interested in becoming users in the future. Okay, so the 2DCC is a materials innovation platform. So the Materials Innovation Platform program is supported by the National Science Foundation, and it was initiated a few years ago by NSF in response to recommendations from several committee reports. So the first committee report was a report from the National Academy of Sciences that came out in 2009, and it identified a need to rebuild the science of crystal growth in the United States. The second one was the Materials Genome Initiative, as you're probably familiar with. So the Materials Genome Initiative came out in 2011, and it identified the potential to accelerate materials discovery by closely coupling synthesis, characterization, and theory modeling. And then the final report is one that came out from the Mathematical and Physical Sciences Advisory Committee at NSF, and it recommended the creation of the materials innovation platforms as user facilities focused on a targeted materials outcome that would embrace the closed loop approach of MGI. And at NSF, the MIPS, or the Materials Innovation Platforms, are part of the National Facilities Program within the Division of Materials Research. So that's a little bit of background about where this platform program is coming from. So I mentioned some of this, but the features of a MIP include the following items. So first of all, the research is focused on a targeted outcome in an area of national importance. And in the case of our MIPS, the focus is on the synthesis of inorganic materials in order to build that expertise up in the US. The MIPS also include a team of researchers who have expertise in synthesis, characterization, and theory modeling, and it embraces this closed loop approach of MGI. It's organized as a user facility so that it provides open access to new materials, synthesis and characterization equipment, theory and modeling tools, and data and expertise. And at least 50% of the time on the MIP equipment must be devoted to research projects that are led by investigators external to Penn State, including researchers at non-R1 institutions. And finally, there are education and outreach programs to advance the mission of the platform, and this webinar series is one of those programs. Okay, so our MIP is focused on the synthesis of 2D materials, specifically layered chalcogenides for next generation electronics. This class of materials consists of 2D monolayers and 2D surfaces and interfaces, which offer transformative new science that can be harnessed for novel devices, including some of those that I've listed here, such as steep slope transistors based on tunnel FETs made out of materials like transition metal dichalcogenides, or topological insulators such as bismuth selenide, which are of interest for a range of spintronic devices, and other heterostructure devices that are based on the stacking of dissimilar 2D materials. So this class of materials includes the transition metal dichalcogenides such as moly disulfide and tungsten diselenide, as I'm showing here. If I can get this pointer to work. So the transition metal dichalcogenides. It also includes group 3 chalcogenides, so things like gallium selenide, or group 4 chalcogenides like tin disulfide, as well as topological insulators that are comprised of bismuth selenide or bismuth antimonide telluride. So our MIP is focused on advancing the synthesis of monolayer and few layer films, as well as bulk crystals of layered chalcogenides, which are needed in order to drive device developments over the next decade. So let me give you an overview of our platform. So our MIP implements the closed loop development, including synthesis, characterization, and theory simulation. The experimental efforts are focused on the development of advanced deposition tools, which are listed here. So this includes, hold on. So this includes tools such as hybrid molecular beam epitaxy, as well as chalcogenide MOCVD. And these tools incorporate in situ characterization techniques such as STM, AFM, ARPES, and 4-probe testing to study the structure and electronic properties of the layers, as well as real-time optical spectroscopy, including Raman and photoluminescence, in order to study and monitor the transition of the films as they go from the monolayer level to few layer films or bulk. And the experimental efforts are supported by a battery of theoretical techniques, which I have listed here. So this includes things such as density functional theory, Monte Carlo and molecular dynamics simulations, as well as reactive force field and phase field simulations. And the aim here is to both understand the growth kinetics of the deposition processes, as well as the properties of the resulting layers. Okay, so let me tell you a little bit about our user facilities. So this is equipment that we are currently purchasing or designing that will form the basis for the experimental facilities in the 2DCC. So our plan is to have one MOCVD system and 2 chemical vapor transport systems operational within the next 6 months. And then we'll be bringing on additional equipment, which will include a multi-module UHV growth and characterization system, a hybrid MBE system for TMDs, a chalcogenide MOCVD system that includes in situ optical characterization, and a Bridgman furnace. And we expect all of these systems to be fully operational by the end of 2017. In the meantime, we have existing MBE and MOCVD tools that we use for the deposition of layered chalcogenides that are currently part of faculty labs here at Penn State. And we're using them to produce samples for users as a way to get started in the MIP user program. And I'll discuss this in more detail later on in my presentation. In addition to the experimental user facilities, we're also ramping up our ability to provide theory and simulation support for the experiments. So we have unique capabilities here at Penn State to model reaction kinetics through the use of REACS-FF. So that's a reactive force field simulation tool. And it can be coupled to first principles and molecular dynamics simulations. So the theory tools will be used to help interpret characterization data that's obtained from the in situ techniques and also guide the experimental plans. And we currently have a call out for user proposals in this area. to assist with the development of theory tools, and I'll discuss this more later on in our webinar. Okay, so let me just quickly go through the organization and the location of the MIP facility. So at Penn State, the MIP is part of the Materials Research Institute, which is the organization that oversees materials research and user facilities operations campus-wide. So the MIP joins 3 other user facilities at Penn State, which include our nanofabrication facility, our materials characterization lab, and our materials computation center. And the majority of the MIP equipment will be located in the Millennium Science Complex, which is shown as the background to this slide. It's actually going to be located on the first floor, right down the hall from the nanofabrication facility. And what's very nice about this is that MIP users will have full access to the equipment, tools, and the staff expertise of these other user facilities. So for example, let's say that a user is interested in studying the properties of tin diselenide tin disulfide heterostructures. So they could submit a user proposal to the 2DCC to get access to one of the MOCVD systems to grow the structures that they're interested in. And then they could use the confocal Raman system and the aberration corrected stem that we have in the materials characterization lab to characterize the materials with the support of experienced research staff. In addition, they could request access to the nanofabrication facility to do lithography and metal deposition, to do electrical testing of the structures. So I think that's a real benefit of the way that we have organized the MIP here at Penn State. And let me just quickly go through the leadership and administration and our overall organization. So the leadership team is shown here. This includes myself, Nitin Samarth, and Vin Crespi, who are the leads for synthesis, characterization, and theory. Josh Robinson is the director of our user program, and Eric Hudson is in charge of our education outreach and diversity initiatives. And you already heard from Kevin Dressler, who serves as our operations and facilities director, and we have Rosemary Biddle, who is our administrative support coordinator. And then this is the org chart for the MIP. So in addition to the leadership and administrative team that I mentioned, I also wanted to point out that we have an external advisory committee that's comprised of experts from academia and industry, and you may know some of these folks. We also have a number of affiliate faculty at Penn State who are part of the user support groups in synthesis, characterization, and theory. So we have a large number of faculty and staff who are involved in this materials innovation platform. Okay, so now let me switch gears and tell you more specifically about our user program. All right, so what are the benefits to you of using the 2DCC? So first of all, you get to join a community of researchers that are focused on 2D materials and devices. The idea here is that we want to build a network of users who share information and data and generally work together to accelerate advancements in the 2D materials and device field. As I mentioned earlier, you gain access to state-of-the-art equipment and expertise, which I have listed here, that can help you advance your research. And best of all, it's free for US researchers from academia and government labs who are doing non-proprietary research. NSF covers all of the research expenses. For industrial and international users who are interested in getting access to the MIP facility, they can do so by paying user fees that are based on cost recovery. And finally, for users from non-R1 institutions, so minority serving institutions and primarily undergraduate institutions, there are some limited funds to cover travel and living expenses for researchers and their students if they would like to visit Penn State and work in the MIP facility. Okay, so we have several different modes by which users can access the MIP. The first one I call a remote mode. So this is basically the standard mode of collaboration where users can request for the 2DC staff to maybe grow particular samples or provide characterization or modeling data in support of their research. And while the remote mode will work for many projects, we encourage users to visit the 2DCC facility and spend time directly working with the 2DCC staff and faculty on their experiments so that they get exposed to the deposition tools that we have, MBE or MOCVD, and also help to build this community of users. And finally, if there are users who can spend an extended time at our facility, they can become trained to operate the equipment independently to carry out their research. Okay, so how do you become a user? So researchers can access the 2DCC by submitting user proposals via our online proposal submission portal. There are two different types of proposals that can be submitted. The first is a proposal for a research project that I have listed here. So these proposals can describe plans for synthesis, characterization, and or theory efforts over a period of about 1 to 2 years. And the goals of the research should align with the scope of the 2DCC in 2D materials for next generation electronics. And they should also align with our capabilities, which, as I mentioned, are evolving over time. So all that's needed here is a 3-page project description. So basically describing the motivation for the research and the technical plan, plus an NSF style bio. And the proposals will be reviewed by experts external to Penn State who are familiar with the particular research area. Alternatively, users can request samples that we fabricate on a more routine basis at the 2DCC for use in their research. And there's a list of available samples on the 2DCC website. The sample requests are much shorter, just 1 page maximum, and they're reviewed internally by the 2DCC staff. And the reason for this is that we want to be able to provide a quick response and get samples out to users who are interested. Okay, the next slide is the user proposal process. So this is a schematic of the user proposal process for the 2 types of proposals that I described. So in the case of research projects, after the proposals are reviewed by external experts, the 2DCC leadership team makes a final decision based on feasibility and time that's available. And then if the project is recommended for funding, the researcher would work with the user support groups to identify the resources that are required and to schedule time on the equipment and arrange travel, if desired, in order to carry out the project. Okay, as I mentioned, we have user support groups. So these groups are comprised of 2DCC faculty and staff, and as time goes on, we hope that we have experienced external users also become part of these support groups, and they're in synthesis, characterization, and theory. And the purpose of the user support is to provide expertise to users and also assist in project coordination and allocation of resources and time on the equipment. In addition, each project will be assigned an internal advocate. So this is someone who will serve as the main point of contact for the user, and they also help to move the project forward and make sure that there is time allocation for the research and that samples and data is sent back to the user. And in addition to the faculty, there are also a number of technical support staff in the 2DCC. So this includes research associates for MBE, MOCVD, and theory, as well as a facilities technician and postdoctoral scholars and a few graduate students. So these are all of the people who are available to interact with users of the 2DCC facility. Okay, so let me tell you a little bit about the call for user proposals that we have out now. As I mentioned, we are ramping up our theory and modeling efforts, and we have a solicitation out for user proposals to help develop these theory tools that will support upcoming experimental studies. So for example, there's a need to develop material-specific empirical force fields for the REACS-FF simulations. And there's also a need for accelerated first principles methods for many of these modeling studies. So these projects would provide support for 2DCC staff and students to work on the project, as well as access to computational resources. And the proposals are submitted via the research project portal that I mentioned, and they have similar requirements to what I previously described. And since we need to get the tools in place during the first year, we've set a deadline of August 31st for these proposals. And I would just want to mention that they should be closely aligned to synthesis efforts in the 2D area. So if you have any questions about this theory solicitation, if you'd like to get more information, please contact Vin Crespi. He's the theory lead in the 2DCC. We also have a variety of standard samples that are available for users upon request, and I have listed them here. This includes transition metal dichalcogenide films like moly disulfide or tungsten diselenide that are grown by physical vapor transport or MOCVD in our existing equipment. There are also films like bismuth selenide, which are topological insulators that are grown by MBE. And in addition, we also are able to provide graphene. So in many cases, there's interest in graphene as a substrate for 2D materials, and we have both epitaxial graphene and CVD graphene layers that are available. And with all of these samples, we provide characterization data, so AFM, Raman, photoluminescence, whatever is most appropriate for the particular sample type, along with the samples. And if you have any questions, please contact me. I'm the lead of the synthesis user support. Also, as I mentioned, this is the first of our webinar series. So these webinars will be held on the last Tuesday of each month from noon to 1 p.m. Eastern Standard Time. And they'll cover a range of technical topics in the field of 2D materials and devices, given both by internal speakers here at Penn State and also outside speakers. In addition, we plan to have webinars on some broader topics, such as diversity and education issues that are relevant to our platform. And I should mention that the next webinar will focus on theory and computation of 2D materials. Vin Crespi will be giving that webinar, and it's scheduled for July 26th. So if there's anybody out there that's interested in the theory solicitation, that would be a good webinar to listen to. And finally, if you want to get more information, I'd encourage you to visit our website, mip.psu.edu. It is chock full of information about our facilities, current capabilities and plans, and also detailed instructions on how to submit a user proposal. So if you think you might be interested in submitting a proposal, but you're not sure if the topic is suitable or if you need more information about the capabilities of the MIP or our other facilities, I strongly encourage you to contact me or any of the other members of our leadership and administrative teams. As I mentioned at the start of this webinar, our goal is really to create a community of users working on 2D materials. So we're really interested in engaging as many people as possible in this endeavor. So with that, I'd like to conclude this webinar. And if there are any questions, please type them in the chat box and we'd be happy to answer them. Okay, we have a question. It is asking, are there limitations to what materials can be grown? For example, excluding certain elements. So at this point, we're really setting up the systems. So we're considering a wide range of different materials. I can't say that there's any particular element that we would exclude, but in general, we want to set up the systems to be able to grow specific classes of materials. And so typically, for example, with the transition metal dichalcogenides, you're usually talking about tungsten or molybdenum or sulfur or selenium. So our systems will be set up to grow specific classes of materials, but we're always interested in interesting science. So if there's an interesting science idea that involves a material that we're not currently growing, that would definitely be of interest and appropriate for a user proposal. So I hope that answers your question.
So there's another question, Joan, about may we have a set of your slides?
Yes, so this webinar will be posted on the 2DCC website. And I don't know if, so I guess you can access the webinar. We can also post the slides on the website as well, if you'd like to download them and share them with others.
And what I also can do, Joan, when I get control of the computer, is to go ahead and upload them here in the file share area. So you see down your lower left, there's a files 3 header. I'll upload the file, so before you log out, it'll be uploaded, and that'll be done after the session is done recording. So you can just grab it directly.
Okay.
It'll be in a PDF, not a PowerPoint.
Okay.
So it's
Yeah.
protected.
Okay. Yeah. So we'll make the slides available. I see that there's another question. So the question is, will there be TMD heterostructure samples available in the near future? So we do have some heterostructure samples available. However, our processes are not developed to the point where we can fabricate heterostructures with well-controlled thicknesses like monolayer heterostructures across large areas. So there's the possibility of getting samples of heterostructures if you're okay working with small areas. So for example, moly diselenide and moly disulfide and tungsten diselenide, those types of heterostructures could be available. So if you're interested, please go ahead and submit a sample request and we'll see what we can do. Are there any other questions? Okay, if there aren't, again, I'd really like to thank everybody for participating. I hope you've heard something that interests you here, because we'd really like to get as many users as we can for the 2DCC, because that's going to help us to really accelerate progress in this area. So thank you very much, and contact me if you have any other questions.
Okay, so hold on for just a few minutes, everyone. I will be loading the PDF of this presentation in the file area where you can download it directly. We will end the recording now.